Welcome everybody to this video, very important one, where we will be finally estimating the parameters of the simple linear regression. That is a regression with one independent variable, one explanatory variable that we will be calling x. If you like this video, please consider subscribing to the Let Me Explain channel, and actually also please consider becoming a member, joining the channel as a supporting member to get access to all the videos available on the channel. Right, let's get cracking with the topic. In the previous video where we introduced simple linear regression, I gave you a very simple example. I'm going to recreate this example right now. That was where we had 4 candidates in the CFA Level 1 exam, obviously completely hypothetical. We called them A, B, C, and D. We jotted down the time spent studying, and this was absolutely fictitious. 40 weeks, 42 weeks, 15 weeks, 30 weeks, and we found that there probably is some relationship between the time studied as measured here in weeks and the score achieved on the exam. So the exam scores were 75% for A, 87 for B, 42 for C, and 70% for D. Now, in a moment, we'll use this data to compute the parameters of the simple linear regression. Before we do that, let's just very quickly jot down the mean values. Now, time spent studying is going to be our independent or explanatory variable that we typically denote with x, and we plot it on the x-axis on a scatter plot. That's what we did in the previous video. The independent or explained variable y, that's going to be the exam score. So over here I've got my x bar and my y bar. Please appreciate that we're treating these 4 candidates as a sample of the overall population. Hence we are using notation that is absolutely appropriate for samples x bar, y bar. That's how you show the sample mean. Okay, let's start with the time spent studying. 40 plus 42 plus 15 plus 30 divided by 4. Okay, 31.75 weeks is the mean time spent studying. In weeks, 75 plus 87 plus 42 plus 70 divided by 4. 68.5% would be the mean score achieved. Now, in the exam, you may be given a set of data like this, maybe a little bit more than just 4 observations, and asked to estimate the parameters of the linear regression in line with what we did in the previous video. Now, the easiest way to do it, and the only way I recommend, although I will walk you through the sort of more elaborate version on paper, just to give you some background knowledge on what your calculator is doing, is to use the calculator. For that purpose, we're going to access the data worksheet and the stat worksheet. So to access the data worksheet, you need to press the second key on your calculator, followed by the digit 7, which has data as its secondary function. So second, data. I've cleared my data worksheet, but just in case yours is full of, well, data, I guess, you may want to press second followed by CE/C. That key has clear work or clear worksheet as its secondary function, and that will get rid of anything that may be sitting in there already. Now, you may in this video see me disappearing on and off because I want to give priority to the calculator in this recording, and sometimes my little window with me, my head in it, will obstruct what I'm writing down and the calculator view, so don't be surprised that I will be popping on and off at various times. That's something I'll determine in post-production, when I appear, when I don't. Right. this is the place where you input the raw data. Now, X for us is the time spent studying, so I will be inputting my first X, that's 40, followed by the enter key, and I've got, you can see my calculator has accepted that this is now the input for my first X. I use the down arrow to scroll down to Y. So corresponding with that X of 40, I'm going to now input the score of 75. So 75 followed by enter. Brilliant. You need to follow this up by enter because that's how you get your calculator to understand, hey, I'm finished inputting the number. Down arrow again, my second X, which is going to be 42. Enter. Down arrow once, 87 for Y. Down arrow again, 15, enter, followed by 42, enter. And then 30 weeks for the final one, down arrow, 70% as the score. Now the nice thing about the data worksheet is that you can scroll up and down, you can check your inputs, like if you're not sure if something was done correctly, you can just go back and forth, examining your inputs, and you can override an input which you find to be erroneous, for example. So your calculator has now stored the raw data. It's time to move on to the worksheet, which is next door, by pressing second followed by 8. 8 has the secondary function of stat. This is where the magic happens. This is where all your calculations happen. Now the first thing you see is lin. Leave it like that. It stands for linear, which is great. And your calculator will tell you, okay, in the worksheet next door, in the data worksheet, I can see that there are 4 observations stored, X and Y values for four separate X and Y values, which is great because we had candidates A, B, C, D, so 4 candidates. The mean of the X's which we inputted is 3175, which kind of confirms our previous entry. Previous computation. The sample standard deviation is 12.33. Okay, we haven't computed sample standard deviation, and the population standard deviation is 10.68. The difference between sample and population comes from whether you divide by n or n minus 1. We don't need necessarily that right now. And then it tells you the same thing for y. The mean value of y was 68.5. The sample standard deviation for y, 1905, and 16.5. As you can see, when you compute the sample standard deviation, it's a little bit bigger than the population one. That's because we divide by n minus 1 instead of over here just by, sorry, went too far. We divide by a lower number, and over here we divide by a higher number, n minus 1 instead of n. Okay, now this is where the interesting stuff comes up. You will see A is your intercept. So the first of the regression coefficients that you need. That is 20.918. Jotting it down. Next one, as I press the down arrow, B, that's the slope of the line of best fit in the linear regression, and that is 1.499, let's call it. If I press the down arrow again, it also gives me R. Now R is not really a regression coefficient as such. I'm still going to write it down. It's 0.97, and this is your correlation. R is correlation as computed on a sample basis, and you can see it's very close to +1, which means we've got a very strong linear relationship between the X and Y variables. That's what correlation is telling us. And if you got such a question, estimate either the slope or the intercept in the exam, this is how you would do it. You'd input the data into the calculator, and hey presto, that's done. Easy. Now, to fully appreciate what's going on in regression, simple linear regression, I still want you to be able to understand the mechanics behind what your calculator does. Because in order to compute the slope and the intercept, your calculator performs relatively simple mathematics, or simple when you've got 4 observations, much more complex when the number of observations is higher. So I want you to appreciate how this is actually done, although you'll probably never have to do this yourself in the exam. To kind of, in the old school way, compute the slope, you would take the covariance between y and x and divide by the variance of x. Now this is good practice if you've forgotten how to compute covariance, variance, kind of going through it at least one more time. Covariance is the sum, starting with the first observation out of the 4 in the sample and finishing with the final one, which is the 4th one, of the following. The product of a certain multiplication, where you take the value for the observed value for y. For example, this is going to be our y number 1, and this is going to be our x number 1, because this is observation number 1. That's going to be observation number 2. Sorry, I should have written x1 here. This is x2, this is y2. So for every observation of the 4 that we've got, we're going to take the value observed for y and deduct from it the mean computed for y, which is that constant 68.5. It doesn't change across the sample. And we do the same over here. We take the value assumed by x in a given row and we deduct x bar, the mean of all the x's. Divide this by n minus 1. That's what you get for sample covariance. And now, so that's our cov term, and variance of x is similar. It's also a sum of the differences, but this time focusing only on x. Take each of the x values, deduct x bar, and if you just stop there, you would get a value of 0, because the mean is a value which makes all the sum of all the differences equal to 0, which is why we square all those differences and we divide them by n minus 1 anyway. Now, however horrific this looks, it may be simplified because you'll have n minus 1 in the bottom of both fractions, and dividing by a fraction is the same as multiplying by its reciprocal. So what this simplifies to is you can actually get rid of these denominators and you can say this equals the sum, starting with I1 and finishing with n. I'm repeating what's in the top of the original covariance term, forgetting the n minus 1 and just dividing by this. Okay. If you're looking for the relationship between two fractions and the two fractions have the same thing in the denominator, you can just focus on the relationship between the numerators. That's essentially what we're saying here. Mathematically, this is absolutely fine. And now we can work with this, although it will take a bit of time, right? It's not an easy thing to do, and definitely something you don't want to do in the exam. So let's focus on the top row. I'm going to go step by step here. I'm going to take for each row separately the value for x, the value for y, and obviously deduct respectively the means. So it doesn't matter whether you start with y or with x. I'm just going to start with x. 40, that's the number of weeks, minus the mean over here, which was 31.75. Let's pull this up so you can see it, 31.75. So minus 31.75, okay, that's 8.25. multiplied by the difference of the y value. That was, I opened the bracket by the way, 75 minus 68.5, close that bracket, equals, right, one difference times the other difference gives 53.625. Please notice that in the case of the A candidate, the two values, the value for X, time spent studying, and the exam score, that's the value for Y, were both above their respective means. If one was above and the other was below, we would get one being positive, one of these brackets or terms in the parentheses producing something positive, the other negative. If they are both on the same side of their means, we get a positive value. So both are above, or indeed both are below. That's why over here we've got a positive sign, which will later determine whether we've got positive or negative covariance, which also determines whether we've got positive or negative correlation. Right, next row, this one now. This is where we've got x2 and y2. Same process. Take the x value, 42, deduct the mean for x, which is the steady 31.75 from the bottom, and multiply this by open bracket 87 minus 68.5, close bracket, equals, right, the next sort of sub result is 189.625, and my job is to add all of these up. Time for the third one. So I'm now in row C. 15, well, this is lower, right? Lower than the mean. 15 minus 31.75 negative multiplied by open bracket 42 minus 68.5 close bracket, also negative, but the result of that multiplication is a positive 443.875. 443.875. And time for one more. 30 weeks minus 31.75 equals negative 1.75. So the time spent studying here was below the mean across the four candidates. However, the score was above the mean, above average. So I'm going to get a negative product of these. 70 minus 68.5, close the parentheses, and I get just 2.625. Now this will have to be divided by xi minus x bar squared. So I kind of have to go and repeat the same thing just for the x's and square. Let's see, well, I could cheat and use what your calculator tells me from the stat worksheet, but I'm going to do it nevertheless. I'm just going to now focus on the column labeled x. So 40 minus 31.75 equals square that. Okay, I'm not going to write the result down because I'll just do this in one kind of go. Open bracket 42 minus 31.75 close bracket, square it, plus open bracket 15 minus 31.75 close bracket, square that, plus open bracket 30 minus 31.75 close bracket, square that, equals, okay, 456.75 in the denominator. Now let's see what this sort of gives overall. Starting from the top, 53.625. Have to be extra careful to get these numbers in correctly. 189.625 plus 443.875 plus, well, actually, minus 2.625 equals, right, just in case I lose this number, let's write it down, and I divide by 456.75, divide by 456.75, well, I've already done it. You can see that the result is 1.499, and please appreciate that having done all this work, it's really time demanding and very prone to errors, we got the slope, which our calculator had previously given us, 1.499. It's the same number. Brilliant. Now, once we've got the slope, let's also calculate the intercept. The intercept, or the official formula for the intercept. So we've got the slope, and now we'll have the intercept. It's actually much easier than that for the slope, but you need the slope first. It's going to be the mean value for the y's minus the slope term times the mean value of the x's. So what was the mean value for the y's? It was 68.5, and 31.75 was the mean value for the x's. I'm taking the numbers from up here. So 68.5 minus the slope, 1.499, times 31.75 weeks was the value for the mean value for the weeks studied. And I'm going to utilize the number which I still have on my calculator display, because if you don't use the precise number, you get the result slightly off what it should be. I'm just going to stick a negative sign in front of it with the plus minus key, multiply by 31.75. Okay, so I effectively now have sort of the tail here, the right hand tail, and I'm going to add 68.5 to it, and we get 20.918. Let's see if that agrees with the intercept term which our calculator had calculated for us. Of course it does. Brilliant. Great. As you can see, it's much easier to utilize your calculator. So in the exam, please do that instead of trying to do this by hand. It really doesn't really make much sense. Now, so that was the core of the video. If you don't have any more time to listen to what I'm going to say next, which are some additional points, go ahead and study something else. I'm going to now talk to you about the properties of some of these terms and computations. Okay. So I will not necessarily need to show you my calculator anymore, because we won't be doing any computations as such. What I want you to appreciate next is that the slope, or the formula for the slope, is very similar to the way in which we compute correlation, with a very important difference that comes in the denominator of this fraction. If you want to compute correlation, that's R, and by the way, our calculator had given us correlation, right, 0.97. What you'd need to do is take the covariance of the two terms, and then instead of dividing by the variance of x, which is this standard deviation of x squared, you'd take the standard deviation of y multiplied by the standard deviation of x, right? Your calculator does show you R, but the denominator, is always above 0. It's always positive, because standard deviations are numbers that are more than 0, right? They are positive numbers. So, and actually variance, being standard deviation squared, is always positive. Therefore, the slope of the linear regression, so the term slope, one of the key regression coefficients, and correlation always have the same sign. And so if one is positive, the other has to be positive as well. And whether it's positive or negative is determined by the sign of the covariance. So this depends on the covariance being either positive or negative. And covariance, as you saw, the sign of it is a function of whether there is consistency in x and y being at the same time above or below their respective means. If one is above its mean, like X over here, 40 weeks studied, being above the mean value for time studied, and the exam score also being above the average, the mean, you're going to get a positive element in the covariance computation. However, if there's discrepancy, one is above, the other is below, or one is below, the other is above, you'll get a negative sign. If both are below, you'll get positive sign. Covariance measures the degree of the mutual relationship, but it's at the bottom of it is whether these two values lie above or below their respective means. This is something to absolutely sort of remember. Now, another thing which is, I think, very critical is how we interpret the correlation coefficients, the intercept and the slope. Interpreting the regression coefficients. So, what is the intercept? Well, if you draw a scatter plot with all the different observations, okay, a lot more than we have, we only had 4. This is our line of best fit. Obviously, this is the y-axis, this is the x-axis, and the intercept is the level of y, that is our dependent variable, when x equals 0. So when x here equals 0 at the start of this axis, what will be the y value? Sometimes this is unrealistic because in many sort of economics or social sciences, you can't assume an x of 0, the lack of something. But not in this case. If we're thinking about candidate score as something that's dependent on the time studied, then surely you can imagine that somebody who hadn't done any studying at all just goes into the exam and picks answers randomly, will still get some positive result, right? A result that is non-zero. So the intercept, which in our case came in at 20.9%, I guess would be the result of a candidate who hadn't studied anything and that had devoted any time to studying, and that is absolutely realistic, right? That this could happen. Now, the slope. This is the change in y, how much y changes. In this case it's positive, but if the slope were negative it would be negative change for a 1 unit change in x. Effectively, if a candidate studies an additional 1 week, what's going to be the incremental increase or change in their score? So in our case, the interpretation would be that 1 additional week of study, and remember we're talking about a linear relationship, so it's constant across all the x's. We're assuming linear progress, a linear sort of steady constant slope. 1 week of study time brings about a positive 1.499. That was indeed the slope, 1.499 here of this regression, percentage point increase in exam score. Of course, please appreciate that I completely made this stuff up. That's probably not the way it is, although I'm quite, I randomly created numbers, but I'm quite happy with the conclusions from them. Right, that's one thing. That's another thing to appreciate. Now, another thing that your curriculum squeezes into this sort of lesson within the within this learning module is data types that we have in regression. You can have a cross-sectional regression using cross-sectional data. Let me tell you what that is. This is when you use, or a regression which uses many observations for x and for y, but coming from the same time period. So you may, for example, be looking at numerous companies, numerous stocks, different indexes, different funds, etc., etc., but at the same time, in the same year, in the same month, and looking at some relationship, for example, in the case of companies, between their results and the amount of leverage they've got on the balance sheet, something like that, and you're looking cross-sectionally in the same time period. On the other hand, many of the regressions that you'll be performing or looking at from an exam perspective are going to be based on time series data, so they will be time series regressions. And these utilize, or this type of regression, so probably I should have singular here instead of the plural, time series regression uses many observations, many observations, obviously for x and y, but from different time periods, but for the same company, the same fund, the same stock, and seeing how it behaves, how something behaves over time when the explanatory, the independent variable changes. That's going to be time series data. Right, and one more note, slightly sort of more abstract, I guess, but nevertheless important, and relating to something I said in the previous introductory lesson on simple linear regression. In the previous lesson, I wrote an expression for the linear relationship between y and x. The y value for a certain pair of x and y is going to be given by the intercept plus the slope multiplied by the x value, and there was an error term as well. Now, very importantly, these b0 and by values were supposed to be the population parameters. The linear regression coefficients as would be computed for the entire population. And the problem is that we can't observe them, cannot observe them, because we typically don't have access to the entire population. We only have access to a sample. You could poll all the candidates in the CFA exam, CFA Level exam, but it would probably be uneconomical, too time consuming, so we take a sample. Probably 4 is not enough, but it's good enough for a little example here. So instead, we use a sample, and from it we try to infer something, make some conclusions. We use a sample and we compute sample-based estimates for the intercept and the slope. We call them B0 and B1, but in your curriculum you'll see a little hat added to the B0 and B1 to show that these are based on a sample. These are the parameters, the intercept and the slope, computed from a sample. And the problem is, if you had a different sample of 4 candidates with their own study time and exam score, you'd probably compute B0 and B1 hat at a slightly different level, because every sample contains different data, or may contain different data, and you get different results. So appreciate that what we do here is we compute a Yeah, we compute B0 and B1 hat in such a way, computed so as to minimize the sum of the squared vertical differences to the regression line, something we discussed in the previous lesson. Effectively, we get a function where we have an estimated value for y, estimated y value based on the estimated relationship between y and x. But because we are using these values computed on the base of a sample, we would say that this is b0 hat plus b1 hat, that's the slope coefficient, times the value of x. Now there will always be a residual. That line which we draw typically doesn't go through all the points unless, you know, there is perfect correlation here. So there will always be a residual. And that residual is labeled EI, and it's the difference between the computed, the observed y value and that predicted from the regression model that you build. But our job in minimizing the sum of the squared vertical differences is basically to minimize something called SSE. This is the sum of squared error. Why we square is something that we explained in the previous video. So the sum of squared error is the sum of, starting with 1, finishing with n, all of these differences. The actual value of y versus the value for y that's predicted under our regression model using the regression coefficients that we got, squared. If we don't square, the positive differences and the negatives offset one another. So we could say that this is the difference between the actual, sorry, I don't need this equal sign here, the actual value of y from the sample and where the regression predicts where we would be, and that's the intercept plus b1 xi, close bracket. This should have been a square bracket here. Okay, so this is basically the sum of all of the so-called residual terms. Let me give you a little bit of context here. For example, the intercept that we've got, 20.918, and the slope that we've got, 1.499, will allow us to predict where a candidate should score if they studied, I don't know, for 40 weeks. So 20.918 plus 1.499, that's the slope, times 40 weeks of study, should produce an exam score of something like 80.878. I'm not showing you my calculator anymore. I'm just showing what would happen if, as xi, we had 40 weeks. We should get the predicted score is something like 80.9%. However, candidate A only had 75. There is a difference between the actual observed value and that predicted by the regression model. That's what we mean by the residual. However, it is this specific intercept and this specific slope that allow us to minimize the sum of the squared differences across the 4 candidate scores. Okay. So let me say that this residual is how much the observed y value, exam score, differs from the y value estimated using the regression line. And y value estimated using the regression line. Okay, and let me just tell you that this is different, absolutely different to the error term over here, right? Because this error term, which I wrote in the previous, in the function from the previous video, this refers to the underlying population relationship. This is the difference between the observed y value and the y value computed using the true underlying population B0 and B1, the true coefficients, which we don't know because we rely on coefficients computed from a sample. There's a, conceptually this is a big difference. In reality, it won't be so much of a difference, but your book talks about it. The difference between the so-called residual, the difference between the observed and what your model predicts, which is based on coefficients computed from a sample, so B0 and B1 hat, versus the error that you would get if you had access to the true B0 and B1.